So this is what a linear equation looks like, or a linear sequence. If we just looked at it like a sequence, you know, 5, 7, 9, 11, we could look at it that way. In fact, we could even write an equation for a sequence, couldn't we? Like using n for the number in the series, right? So how does that look? Do you guys remember, like a sub n would equal 2 times n plus 3? So if we wanted to find like the 10th number in this series, if we wanted to find a sub 10, 2 times 10 plus 3. So what's the 10th number in this series?
23.
There you go. It's 23. Okay? And this is what we've been working on since 6th grade? Would you say?
Yeah.
Okay, so 6th, 7th, 8th, 9th, we've been talking about linear equations all the time. I don't know why that printer keeps coming on and off, but we're going to turn it off. So, okay. Well, what about equations that aren't linear? I'll make this one in red because it's going to be a little different. Now, there's lots of different types, but we're going to talk about one type specifically and just kind of focus on that. And for one reason, it's kind of similar, okay, the way it works, and so that should help a little bit here, okay? So it'll look like this, like we got when x is 1, when x is 2, when x is 3, when x is 4, when x is 5. Let's see, we got a 5, then we have a 10, then we have, what do you think the next one's going to be? 20. What do you think the next one's going to be? Oh, 40. There you go. And the next one? Okay. So I just want you to know, we do not have a common difference. We are not adding the same amount each time. And by the way, sometimes we add a negative, don't we? So you think of it as subtraction, but we're still adding a negative. Here, though, there is not a common difference. You know, here we add 5, then we add 10, then we add 20, then we add 40. Okay? And that's a hard way to explain something. So tell me a simpler way. How are we getting to each one? How do we get the next one? Yeah, we're doubling. We're not adding 2 each time. What are we doing? Yeah, or so we're timesing by 2, aren't we? Okay. So in this case, we have what we call a common ratio. Okay? So it's not a common difference, it's a common ratio. We're multiplying by something each time. Okay? And so I need you to recognize that here we have a common difference, here we have a common ratio. And whenever you see a common ratio, we have what's called an exponential function. Exponential. You're going to see why we call it an exponential equation or exponential function later on. So here I'll do another one. I don't know why I'm doing them this way. Draw just a t-graph, but 1, 2, 3, 4, 5. Let's see. 90, 30, 10, 10 over 3. What's happening each time? Okay, so you know over here how we said sometimes we add a negative, right? Well, here we're not going to talk about dividing. I want to know what I'm timesing by. So here we'll say, oh, I'm adding a negative 5 each time. Okay. Here it's kind of the same idea. I don't want to hear, oh, we're dividing by 3 each time. What's another way to say that? Yeah, we're multiplying by a third. Okay? So the common ratio here is 1/3. Okay? So we're not dividing by 3. Well, we are, right? But we are multiplying by a third. And this is the number that we need in order to write the equation. Okay? So it's still a common ratio. We're still timesing by something each time, right, Jem? which means it's not a linear equation. What is it? Everybody say it. Exponential function, or an exponential equation. That's right. Okay. So first thing we got to do is recognize a series and what it looks like. Okay. Now let me show you what an exponential function looks like. Okay. Can you guess why this one's called an exponential function? Yeah, look where the variable is. Where's the variable? Yeah, in the exponent, right? Okay. So, first thing we got to make sure of. We don't want to do freshman math on this. Okay? I want to evaluate this when x is, say, a 3. Okay? So I think you guys can all do this in your head. Can you just do it in your head for me? And then we'll see if you're doing freshman math or real math. Okay, so when I do it in my head, I get 32. Now, if you got a really big number, you might be doing freshman math. Okay, so think about order of operations. Okay, what comes first, exponents or multiplication? Exponents, right. So when we do this, you've got to make sure that you're going 2 cubed, which isn't 6, right? 2 times 2 times 2 is 8. And then you're going 4 times 8 is 32. Okay, you cannot go 4 times 2 is 8 and then go 8 to the third power. That's not the same thing, is it? 8 times 8 times 8, that's way more than 32, isn't it? Okay, completely different thing. So let's make sure that we're doing it in the right order. So this is what an exponential function looks like. Look quite a bit different than y equals mx plus b, but kind of similar. We still got an x and a y, I guess, don't we? Okay. If I make a table for this one, let's see. When x is 0, what's 2 to the 0? 1 times 4?
8. Oh wait, what did you say?
Okay, 4. Let's put a 1 in. 2 to the first power. Come on, you're not playing the game. 2 to the first power? 2 times 4?
8.
Oh, there we go. Okay, put us 2 in there. 2 to the second power. 4 times 4? 16. Okay, and we already did 2 to the third power. It was 32. Can you guys see a common ratio here?
Yeah.
What is it?
Times 2 again.
Timesing by 2. Can you see the number we get when we put 0 in?
4.
Now, this seems to me a lot like a linear equation. We have a number we get when we put 0 in for x, like a y-intercept, right? And it is a y-intercept, 0, 4. And then we have what's happening each time. But we're not adding 2 each time. What are we doing? We're multiplying by 2 each time. Okay? So this equation, which you guys want to have in your notes right now, okay, it looks like this. Y equals a times b to the x. So it looks a little different than our y equals mx plus b, but it just gives you a framework. So every one of our exponential equations, our exponential functions, are going to be in this form, okay? Kind of like y equals mx plus b, but y equals a times b to the x. And every single time they're in this form, a is going to have a certain value, or it's going to be a certain thing. What is it in this case? We put 0 in, we get 4 out. 0, 4. So that number right there in front, that A number, what is it every single time?
X.
Is it X? It's the y-intercept. Yeah.
Oh, wait.
It's the y-intercept.
You're good, man. Next question.
Yeah, so doesn't that sound familiar? The y-intercept? It's just like B in our linear equation, isn't it? Okay. And then B, it's not the common difference, it is the common what?
Ratio.
It's the common ratio, right. Common ratio. So if you know the y-intercept and the common ratio, all you got to do is put them here and here, and there's your equation every single time. You just got to put in the number for A and B. Just like up here, we put in the slope and the y-intercept. We had our equation, right? So it's simple. It's kind of similar the way it works. They look a lot different, and they definitely grow differently, don't they? Yeah. If I add 2 every time, is something going to grow super fast? Like every day, I make $2 more than the day before. That's a lot. That's a lot more, right? But what if every day I make 2 times more than I made the day before? That's a lot, isn't it? That's a lot. That's a lot. So this is an exponential function. So you guys are we'll do that. We'll do that part later. Okay. So what do we have to be able to do? Let's see. We've got to be able to look at an exponential function like this and evaluate it for a certain value, like when x is a -2. Okay? So, you guys think you could do this? Can you do this on a calculator? Now, I'm going to show you how to do it without a calculator. It's just y equals 3 times 0.5 to the -2. We're just going to plug that in. Okay? 0.5, which is a half, to the -2 power. I think it's 4. Does that seem weird? How the heck do I get 4? Let's think of it as a half to the -2. Wouldn't that be 2 over 1 to the +2? Which is 4, isn't it? And then 4 times 3?
12.
Okay. So when x is a -2, we get a 12 out. Now let's try to make that work on our calculators. You got your calculators? So it was 3, and I am going to use parentheses, times 0.5 and parentheses. Now how do I raise it to the -2 power? What button do I hit now? See that up caret? Yeah, that's right. Jen even had the symbol. There we go. Okay, up caret, and then you have to use this negative symbol. You can't use the subtraction symbol. You have to say -2. That work? Everybody get 12, okay?
What do you mean, man?
You can use this one.
Oh, wait.
You need one? Oh, you got one? Here. You need one, Dane, too? Okay, you guys might have to share a little bit. You need a calculator, guys. And remember we were supposed to ask Santa.
I got one, but I lost it.
You got one, but you lost it. Oh. Okay. Now, since we're in learning mode, let's learn. Y equals, I don't know, 2 times, no, let's not do that one. Let's do 4. 4 times 2 to the x. I'm going to graph this. You're going to help me. Okay? Now, do you guys really know what this looks like?
No.
Okay. anytime we don't know what an equation looks like when we graph it, and we have to graph it, we just make a table, we get a bunch of points, and then we graph the points until we can see what it looks like. Okay? So, all right, here we go. We need some points. So what's a point you want to put in for x to start off with?
0.
Oh, I've taught you to be lazy. I'm so happy. Okay, we put in 0. Now, 2 to the 0.
0.
No! 1 times 4? Okay, we got to be careful. We've got to know that something to the 0 power is 1, right? Okay, so there's a point, 0, 4. Do we know, hey, wait, that's the y-intercept.
Hey.
Wow.
4. 4. Remarkable. Okay, now, usually I tell you, don't put in 1 and -1 and so close together. In this case, we are going to do that. We're just simply going to put in a 1.
That's an 8.
8.
Math.
1, 8. Let's put in a 2. 16?
Yeah.
Yes.
Okay, 16. Well, that's even hard to graph, isn't it? It's up here somewhere. So this thing, do you think it's a line or do you think it's kind of curvy?
It looks curvy.
Yeah, it's curvy. Okay, so it's going to turn a little bit like this. Okay, now stuff's going to start getting weird. All right, let's put in a different number. Let's go the other direction. -1. Now, 2 to the -1.
Isn't it positive?
Yeah, I hear some of you saying it. So 2 to the -1 is 1 over 2 to the +1, isn't it? It's 1/2. Okay? So 2 to the -1 is 1/2 times 4. It is 4 halves. It's 2. So -1, 2. So we still got this kind of curve going on. Okay, now let's put a -2 in. Do it.
1.
1?
Yeah. 0.
Are we agreeing?
Yep.
Okay. 2 to the -2 power. Should I write it over here again? 2 to the -2 power is 1 over 2 to the +2 power, which is 1/4. So we have 4 times a 4th, which is 1. Okay. So we have a 1. So we put a -2 in and we get a 1. Okay, put a -3 in.
0.5.
So a half?
Everybody
Everybody make that work?
Yeah.
Come on, make it work. I don't see you typing. I don't see you pushing buttons. Put a -3 in. Do you get 1? Or do you get 1/2?
I got a half.
Working? Okay. So a half. So we put in -3, we get a half. Okay, put a -4 in.
0.25.
You guys are already ahead of me. So isn't that a fourth? Isn't that a fourth?
Yeah.
So a fourth. Put a -5 in.
1.5.
That's an eighth. I just want you, look at the pattern here, guys. 1, which is 1 over 1. 1/2, 1/4, 1/8. Then what's it going to be? 1/16.
Never gonna be 0.
What? Dustin, what did you say?
That is never gonna be 0.
It's never going to be 0 or less than 0. It's not going to happen. It does not matter what number you put in for x, you're not going to get to 0. You can get a 32nd, a 64th, 1 over 128, 1 over 256, 1 over 512. It's going to get closer and closer and closer. But it has a limit. So its limit is 0. We're never going to get there. So this thing comes down and it gets dang close to 0. It gets infinitely close to 0, but it never gets to 0. Okay? And that's That's the general shape of every single one of these whenever your common ratio is greater than 1. Whenever it's greater than 1, you're going to get this kind of look to it. You know, the y-intercept could be different. It could maybe not grow or shrink quite as fast. Okay, so it could be more like that. It could be really super steep and come way down here and then turn a little quicker. Okay, but they're always going to have that same general shape. Sometimes they almost look linear. Okay, depending on the common ratio. But whenever the common ratio, whenever this number right here is greater than 1, it's going to have this general shape to it. Okay? So, the common ratio let's just do an easy one. When the common ratio is less than 1, so it's between 0 and 1. Our common ratio, it's never going to be negative, just so we know. We're never going to multiply by a negative right here. This common ratio is going to be a positive, as long as it's an exponential equation like we're talking about right here. So let's make a table. Okay, what are we going to put in?
0.
What's going to come out? Agreed?
Yes.
1 times 3. Everyone? Yeah?
Yes.
Fortune? Yeah? Okay. So 0, 3. So our y-intercept, right? Okay. So let's put in a 1. What comes out? What comes out? I heard a couple of you be brave. 1. Do you see how this one's not growing? What's it doing? We don't call this so this one we call exponential growth.
Yeah.
This one we call exponential decay. All right, and we'll talk more about why those words are important and why we use them. Okay, let's put in a 2. A third?
Yeah.
2 gives us a third. Do you see our pattern?
Yes.
We're timesing by a third each time, aren't we? Okay, so if I put in a 3, 1/3 times a third is 1/9. So when we get out here to 3, then we're getting close to 0, aren't we? Okay, so if we go back the other way, if we put in a -1, so if we go back this other direction, we're not multiplying by a third, we're actually multiplying by 3, aren't we? We're getting bigger. So when you put in -1, 1/3 to the -1, here, should we get out our work paper here? 1/3 to the -1 is 3/1 to the +1, which is just 3, isn't it? And then 3 times 3? 9, okay. So we're up here at 9. So -1, 9. If I put in a -2, it's just going to be 3 times bigger, isn't it? So 27. So -2 is so high up there we can't graph it. So it's coming down here. And here's a case of exponential decay. So I'm going to give you an example of a exponential decay. All right. So here's something that happens in real life that we can talk about with exponential decay. Let's say I buy a car. How much do you think that car costs? 100,000? Boom! I'm on that car. Heck yeah, 100,000.
I would buy 69 Chargers.
So at time 0, this car, it costs $100,000. Okay, when I buy it at time 0. Okay. Now, every year that I own this car, do you think the value of the car is going to go up or go down?
Down.
Down. How can you guys give me a percentage how much you think a car goes down? 5%?
No, 30%.
You think it goes down 30%?
He said 3. You guys are getting big numbers.
Oh, 3%.
I think the Luke was correct.
You think Luke was current about 5%?
Depends on the car.
2.3.
Depends on the car. Good, good.
Yeah, if it's a old car, it'll go up.
Yeah. Now, most cars don't go up immediately. Every car you buy, its value is going to go down initially, and it's going to go down in an exponential decay type of function. So I'm going to make this one, I'm going to say it goes down 10%. Just because 10% is an easy number to work with right now. But here's the thing. If it goes down 10%, what percent do you have left over at the end of the year? If something's 10% off, what percent do you have to pay still? 90%. Okay, so that's what this equation is going to look like. This is how much our car is worth. It's worth $100,000 times 0.9, because it goes down. Luke, Aislinn, stop. Don't go any further. Okay, so it goes down 10% every year. So I have 90% left over. And T, guess what T stands for? Time in years. So how many years go by? Okay, and so as we look at the value of our car, here we have time, and here we have the value of the car. At time 0, what's our car worth? $100,000. After 1 year, $90,000. That was easy. Okay. After 2 years, I think it's going to be $81,000. Do it. To get out your calculator, guys. 0.9 raised to the second power times 100,000.
$81, 3 zeros.
Yep, that's right. Yep.
So I thought to myself, well, it's going to go down 10,000 or 10%. I know 10% of 90,000 is 9,000, so I know it's going to go down 9,000. So this next time it's going to go down 8,100. So after 3 years, give me a number. 72,900. After 4 years, 63,000 ish.
Yeah.
Okay, after 10 years. Can you guys do 10 years for me?
Yeah.
34,867.
32,857.
I thought he said 34.
That doesn't matter. It's close. After 20 years.
20? I'm not having a problem.
Sure, there's lots of cars out in the parking lot that are 20 years old. It's like every teenager's
12,100.
12,100. Okay. So my question is this car ever going to get down to where it's worth 0?
No.
Yes.
According to our equation, though, will it ever get down to 0?
No.
Even after 100 years or 1,000 years, is it always going to have a small bit of value left?
Probably.
Okay, and that's kind of a real thing, because even when a car won't run anymore, does it still have some value in parts and stuff?
Yeah.
Okay. Even when it's an old rust bucket laying out in the dump, could you still recycle the metal out of it?
Yeah.
Yeah.
It's like scrap.
And so now this is theoretical. Realistically, it might cost me more to haul it to the recycler than I could get for the car. Okay? But according to our model, theoretical model here, the value of the car is never going to get down to where it's $0. Okay? Even after 8,000 years, it's worth, a part of a penny of something, right? So this is what we have with exponential decay. Okay? Now let's do exponential growth. Okay, so I am in a Disney movie,
Oh no.
and I don't know. I'm not in a Disney movie. I hate Disney. We're not going to do that. I'm in my own dang book that I wrote, and in this book, the princess gets kidnapped by the dragon, and the king really wants her back, and so he's like, if anybody can save her from the dragon, then I will give you half my kingdom, half of everything. Okay? So Shrek shows up, right? I don't know. And maybe the donkey. Hey, focus. And he's like, okay, I can do this. And so he goes out and makes friends with the dragon and gets the princess back, right? And the king's like, okay, you can have half my kingdom. But Shrek is smart. And he says, you know, you don't have to give me half your kingdom. It's the amount of money you give me. How about today, at time 0, you just give me 1 cent. And then each day for a year, you just give me double that for a year, and then we'll call it good. So we're going to double it each day, and then this will, and for time, right? For how many days? 365. Okay, we're going to do that for 300. So it's going to look something like this, King. Here's time. Here's money. Time 0, 1 cent. Tomorrow you're going to give me 2 cents, and then you're going to give me 4 cents, and then you're going to give me 8 cents. Good. And then you're going to give me 16 cents, and we're just going to do that for a year, and then we're gonna call. Okay.
Not enough money to buy his own kingdom.
And instead of giving me half the kingdom, and so the king's like, done. You're an idiot. I'll take that deal. I got the princess back. I don't have to give you half my kingdom. I'm just going to do this. So what I'd like you guys to do is just figure out at the end of the month, 30 days. Plug it in.
He'll have more than enough money just to buy his own kingdom.
What are you holy cowing about?
Mr. Caller,
Huh?
at the end of the year...
Wait, we're not there yet.
You're not here. The calculator's not working.
Holy cow! Isn't that the end of the month?
Yeah.
Here, let me write that down. Hold on a minute here. 107,418.24. Well, that's only $10,737,418.24.
That's still a lot for a month.
That is a lot for a month. In fact, I'm guessing about halfway through the month, the king started thinking, "Hey,
No back.
what is going on?" And you know, I think if we
The number's not possible.
I think if we do this for a couple months, maybe 62 days, they're each 31 days this time, my calculator starts writing the number in scientific notation. So this E16, yours might say times 10 to this power.
Yeah.
What that means is the decimal needs to be moved over how many times? 16 times. So this number, this E16 means times 10 to the 16th power. That means if you multiply this by 10 to the 16th power, that's going to move the decimal 16 places. Okay? So that's a fairly large number.
Write it down.
So after 62 days, we're talking 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 decimal.
How much is that?
I don't even know.
You want to try and save for us? After a year, the numbers
That number is technically what we would call a buttload.
I don't think there's
A lot. It's a lot. Now, hold on. What?
Doing that every day.
like that's just what he owes.
So we're just doubling each day, yeah.
So like you can. Wow,
Wait, shh. What?
you answered.
All right. Okay. So 1 cent. Yeah. times 2 to the 365.
Yeah, got it.
Number
Now.
doesn't exist.
Here's what my calculator just said. That's such a big number that my calculator is broken now.
What the heck is the second?
It doesn't, it's too big. I can't do it. Okay? This is exponential growth.
Wow.
So this is what I need you guys to understand about what exponential growth. When things grow exponentially, okay, then are they growing kind of fast?
Just a little bit.
It depends.
Or are they growing really fast? Okay. So exponential growth, we see this in nature. If you have a cell and it grows and gets all the nutrients it needs, and then it splits into 2 cells, right? And then each of those 2 cells grow, and eventually they split. They each split, and we have 4 cells now, right? And then they grow and get all the nutrients they need, and pretty soon they split again. This is exponential growth. This is how a baby starts to grow. You have a cell, right? And then that cell gets all the nutrients, everything it needs. It splits into 2, and then they split into 4, and then they split into 8, and they split into 16, and we have exponential growth.
You're just telling me I'm numbers on
However, listen, this is important. Exponential growth is not sustainable. If that baby kept growing at that rate, not only would the mother explode after, I don't even know, a week, okay? But if it kept growing, the mother would be the size of the earth, like in a month. It's not sustainable. It's too fast, okay? Things cannot grow exponentially for very long. Because what do you guys say? There's not that much money in the world? Yeah, I mean,
Isn't that how far it could get where it is?
We're like,
fortunately, we're not that far, but close. Okay. Well, other things that grow exponentially. Animals, the number of animals, like the number of mice, can grow exponentially.
I don't like those.
Okay? So, I just want you to think about this for a second now. Listen. We have 2 mice. They have 4 babies. And then it's only like less than a month later, those 4 babies can have babies. And the 2 that had them can have more babies. And if there's enough food,
They can have more babies.
they can keep growing like that. The number of them can continue to grow exponentially.
But can't they?
And that can lead to bad things. And I want to show you a video.
Overpopulated.
bunnies can do that.
That's why we hunt.